Good afternoon, and thanks to ICAS for the invitation. And thank you also for the kind introduction today. I'm very pleased to address you today, albeit remotely. I'm joined by two of my colleagues. Firstly, Sebastien Dubois, head of the Clean Sky 2 program unit, who will introduce some of the key projects within our current work program and report also about the progress we have made towards our environmental goals. And secondly, Manen, head of our strategic development unit, who will tell you more about what the future has in store for us, especially with regard to the identified future challenges for aviation and the measures we are planning to engage in. This part of the presentation will also highlight some of the main aspects of the new European research program, Clean Aviation, which is going to be launched at the end of this year. The title of our presentation, Clean Sky Towards Climate-Neutral Aviation, says it all. The ultimate target for aviation has been formulated, climate neutrality by 2050. The question now is, what can the running Clean Sky 2 program and the new Clean Aviation program contribute to achieving this target? First of all, and specifically for those of you who aren't so familiar with Clean Sky, let me give you a brief overview. Clean Sky is a public-private partnership bringing together the European Union and the European aeronautics industry, research organizations and universities. We are working on innovative technologies for cleaner aviation with the aim of reducing CO2, NOx and noise emissions from aircraft by 20 to 30%, all versus the best aircraft operating in 2014. To achieve this, we are exploring radically new aircraft configurations, eco-friendly engines, and on top also new system technologies and airframes. We are focusing on innovations for larger passenger aircraft, fast rotorcraft, as well as regional aircraft and small air transport. With over 940 participating entities in 30 countries, we are proud to say that we are a high-performing European-wide ecosystem, finding expertise in every corner of the continent, and beyond, as we also have, for example, Russian or US entities participating in our program. We see this international cooperation as key in order to achieve our objectives. Our projects benefit very much from the innovative competence of the SMEs, the cutting-edge knowledge of academia and research centers, as well as the market-driven expertise of the aeronautics industry. Over 5,000 individual scientists and engineers are involved in our projects. As a public and private partnership, Clean Sky can leverage this expertise in order to maximize effects. We bring together the best of both worlds, public and private, for optimum results. Clean Sky is agile and works efficiently, as we are very close to the scientists and researchers as well as to policymakers. This lets us deliver scientific excellence and innovation across a key industrial sector like aviation quickly, and also ensure that research is oriented towards the right priorities, bringing real added value to the economy and the society. We are also contributing to the post-COVID green recovery. Aviation was hit particularly hard, as you all know very well. But this is our chance to build aviation back better and put sustainability high up the agenda. With this extensive research ecosystem in mind, let's take a look at our current work and some of our concrete achievements to date, as well as how we can maximize these results for future integration into the next generation of aircraft. Clean Sky 2 is building on the work done in the Clean Sky 1 program, which ran from 2008 to 2018 with a total budget of approximately 1.6 billion euros. Clean Sky 2, now under the Horizon 2020 research program, will run until 2024 and has more than doubled the volume of Clean Sky 1 with an overall budget of 4 billion euros. Clean Aviation, the new program, is currently targeting to perform research work for an overall volume of approximately 5 billion euros. You can see here a few examples of technologies that were developed under Clean Sky and Clean Sky 2, as well as two of Clean Aviation's future main thrusts. Under Clean Sky 2, we have pushed the boundaries and developed and ground-tested a counter-rotating open-rotor engine architecture, providing for an unprecedented engine efficiency, although with some integration challenges. We have developed and flight-tested a laminar flow wing concept on an iconic Airbus A340 flight test bed aircraft, a true breakthrough for laminarity on a commercial jetliner. We have completed flight tests for ALPS, the advanced low-pressure system engine concept, with composite carbon titanium fan blades for the advanced and ultrafan engine. All examples of technologies which have pushed the boundaries in various aviation research fields. Within Clean Sky 2, we are now preparing technologies for two radically new rotorcraft concepts, Racer, a compound helicopter enabling vertical takeoff and landing, but with a targeted cruise speed in excess of 400 kilometers per hour. And the next generation tilt rotor, bridging the gap between traditional helicopters and fixed-wing aircraft, with flight tests planned for 2022 and 2023. Another example of a radically new concept within the scope of Clean Sky 2, the multifunctional fuselage demonstrator. An 8-meter-long fuselage barrel which targets a weight reduction of 1 ton and a cost reduction of $1 million per shipset. An example from our propulsion-related Clean Sky 2 project portfolio of key demonstrators is the so-called UHPE, the Ultra-High Propulsive Efficiency concept, focusing on technologies like boosters, low-pressure turbine architectures, and enhanced gearboxes. Finally, 2 focus areas of our new program, Clean Aviation: hybrid or fully electric propulsion and hydrogen propulsion. Electric propulsion or hybrid propulsion for more regional aircraft applications within the indicated time frame. And secondly, hydrogen propulsion via fuel cells or via direct burn of hydrogen in aircraft engines, targeting the replacement of shorter range kerosene-powered aircraft with hydrogen-powered aircraft. This could result in approximately 40% of the aircraft fleet in 2050 being hydrogen-based. The remaining 60% will be powered by sustainable aviation fuels. As I indicated already, Clean Aviation, the successor to Clean Sky 2, will be formally launched later this year. We are going to need more resources than ever before to reach the ambitious environmental target of climate neutrality by 2050. We estimate that totally we'll need 12 billion euros as a minimum amount of investment for research and innovation by private and public stakeholders in Europe up to the end of this decade. Time is of the essence, so let's be hopeful, but let's not underestimate the urgency of our mission nor the scale. A lot of scientific and engineering work must be done before those technologies are market ready, and the time has come to ramp up our green aviation research activities. The EU has set the objective of overall climate neutrality by 2050. What does that mean concretely for the different sectors? This is shown in this colorful graph here. Overall, the dotted red line is indicating the challenge. By 2050, the net greenhouse gas emissions in Europe over all sectors shall be zero. Aviation is part of transport, the olive-colored area. The challenge is clearly formulated. In order to better understand how this can be achieved, let's move over to the next graph. The top of the colored areas shows the hypothetical emission growth scenario up to 2050. The dotted lines at the bottom show the target, a gradual reduction to zero CO2 by 2050 within the EU and slightly higher at global level. What are now the levers for improvement to achieve zero CO2 by 2050? 3 main change drivers have been identified. They are shown here with different area colors. First, reduction of aircraft fuel burn through new aircraft technologies with an improvement potential between 30 and 50%. Second, improved air traffic management and operations with the potential of lowering CO2 emission by approximately 10%. And finally, new sustainable aviation fuels with a potential of approximately 40%. Implementing those measures will have the effect that CO2 emission in Europe will not rise, but will follow the gray dotted line and be reduced to zero. I would like to draw your attention to the remarks at the top of this graph. In order to reach the ambitious goal, new aircraft need to be introduced into airline fleets from latest 2035 onwards to allow for the replacement of older aircraft before 2050. These new aircraft require revolutionary new technologies, and those need to be developed between now and the end of this decade. Time is of the essence. But fortunately, we are not starting from scratch. We can build on technologies being developed within the Clean Sky and the Clean Sky 2 programs, as explained before. You will hear more later from my colleague Ron van Manen on the specific challenges of Clean Aviation program. But first, I give the floor to my colleague Sebastien Dubois to go into more detail on Clean Sky 2. Over to you, Sebastien.
Thank you very much, Axel, and good afternoon, everyone. Let me thank you for your invitation and for the opportunity given to me to present the Clean Sky 2 program, its recent achievements and the perspective. This presentation will deal with the following aspects. What were the aims set and where are we today? The overview of the main demonstrators as implemented in the Clean Sky 2 program, their first assessment of the results and the progress to date. The Clean Sky 2 program to date, this is more than 34 flagship demonstrators, more than 106 demonstrators contributing to these flagship demonstrators, and more than 1,000 technologies. The activities, as implemented in the respective domains of the programs, are organized around 7 main areas of intervention, which are considered essential to deliver the Clean Sky 2 high-level objectives. From the top to the bottom, we can mention the next-generation cockpit systems, the advances in wing and aerodynamics, the optimal cabin and passenger environment, the novel aircraft configuration, breakthrough in propulsion efficiency, innovative structures and production systems, aircraft non-propulsive energy and control systems. The contribution of the demonstrators to the Clean Sky 2 high-level objectives is assessed through, on one hand, the progress towards their maturity level expected at program end, and the estimated benefits expected at aircraft level through the technology evaluator. Our objective remains to meet TRL 5 at program end for more than 75% of the demonstrators. It's worth noting that a huge effort was made in 2020 by all the participants to the program to maintain more than 80% of their pre-COVID objectives at stake amid the COVID-19 pandemic. The COVID-19 had limited impact on the implementation of the activities thanks to the implementation of several mitigation measures. We experienced an average delays of 6 months in the implementation. I will provide you later more details for some of the flagship demonstrators and their contribution to the Clean Sky 2 high-level goals. Let me provide you now with some metrics with respect to the program implementation to date. Approximately 550 grants have been implemented within the Clean Sky 2 program since the program start. 75% of the total effort was spent at early 2021, 3 years before the program end. We are accelerating the path, and we expect to be between 85 and 90% of effort spent at the end of 2021, with most of the design phase completed and the vast majority of demonstrators being in the assembly phase process. Less than 1/3 of our projects are currently closed, and 40 more projects should be completed by the end of the year. Early 2021, 13 demonstrators were completed, and 18 are expected to be completed by the end of this year. That will represent 30% of the total number of demonstrators. 13% more are expected to be completed in 2022, and the remaining 40% in 2023. We are just at the start of our delivery phase. Dissemination and exploitation, we have spent a significant effort on this domain in order to make the results visible through our continuous effort. More than 2,000 dissemination activities are completed to date, including approximately 1,000 technical and scientific papers, and 277 patents have been filed. Let me provide you with explanation of the different flagship demonstrators. I will start first with the domain breakthrough in propulsion domain. Here is presented an abstract of some of the key major demonstrators in this domain. The first one is the ultra-high propulsive efficiency demonstrator, which is led by Safran. This is a technology demonstrator for the next generation of environmental friendly gas turbine for short medium range commercial aircraft. It consists of the design, development, and ground test of an engine demonstrator for an ultra-high bypass ratio engine, higher than 15, with the aim to validate low-pressure modules and systems, nacelle technologies, and transmission system. Different concepts, with and without nacelle, are under investigation. One is about integral drive turbofan. The second is an integral drive variable pitch fan layout with short nacelle. And the third one is an edited single fan. The next step is to select, early 2022, the engine architecture to be tested by the end of the Clean Sky 2 program. The UHP demonstrators aim to reach TRL 5 by 2023 and to reduce fuel burn and CO2 up to 9% as compared to 2014 engine generation, which is the LEAP engine installed on the A320neo. It also aims at reducing noise and NOx in order to achieve the high-level goals. The second demonstrator is the very high bypass ratio large turbofan engine, which is led by Rolls-Royce. This demonstrator is a technology demonstrator for the next generation of environmental friendly gas turbines for large commercial aircraft. The trend to very high bypass ratio engines required technology development across a broad range of complex gas turbine systems, from fan inlet through the complete compression, combustion, and turbine to exhaust. Parallel to the technology development, an engine to demonstrate key technologies at a scale suitable for large engines is being designed and developed to perform ground test and flight test together with Airbus. The Rolls-Royce Advanced 3 core engine will be demonstrated and provide the core gas generator used for the demonstrator. The ground test will start in 2021 and will be performed in a modern installation, Testbed 80, recently inaugurated by Rolls-Royce. The UltraFan aims to reduce fuel burn and CO2 by more than 25% compared to Rolls-Royce's first-run engine. The demonstrator aims to reach TR6 by the end of 2024. Another flagship demonstrator is the TEC-TP, led by Safran. The TEC-TP engine demonstrator project paves the way for a sustainable, low-fuel and low-noise engine for business aviation and short-range regional application up to 19 passengers. The TEC-TP aims to validate the technologies required to develop a new generation turboprop engine that will feature a compact, lightweight architecture as well as offering 15% lower fuel consumption and CO2 emissions compared to the current engines and a noise reduction of 5 dB. The demonstrator aims to reach TRL5+ by the end of 2021. Another one is the Maestro demonstrator, which stands for More Advanced and Efficient Small Turboprop Engine project. This technology demonstrator, led by GE Aviation, for the business and general aviation markets, will aim to deliver validated compression, combustion, and power turbine systems for small turboprop engines, as well as optimized propeller. It aims at reducing CO2 by 18%, NOx by 24%, and noise by 10 decibels noise reduction. TR5 was already achieved in 2020. Full engine is already undergoing flight test. Another area of interventions is advances in wings aerodynamic and flight dynamics. The first flagship demonstrator is Adaptive Wing Integrated Demonstrator Flying Testbed 1, led by Leonardo Aircraft in the regional aircraft domain. The FTB1 demonstrator will allow the integration and flight testing of innovative technologies for a new generation of wing and advanced flight control systems. The demo aircraft will be used to test in flight two different wing aerodynamic configurations, both introducing a wing load control and alleviation system. The first one will be an innovative winglet with two movable, morphing surfaces at the trailing edge, and the second will be an innovative wingtip having an active variable trailing edge tab. The demonstrator aims to reach TR6 in 2022. The second one is called the Flying Testbed 2, which is led by Airbus Defence and Space in the regional aircraft domain. The FTB2 is a flying testbed demonstrator derived from a C295 aircraft platform. The objective of the demonstrator is twofold. The first one is to develop a specific advanced regional aircraft concept optimized for multi-mission purposes flights. The second is to demonstrate the implementation and integration of different innovative technologies at aircraft level. A new semi-morphing wing is designed, manufactured, and equipped with new structural solutions strongly integrated with advanced new control surfaces, flaps, and composite winglets. The Flight Testbed 2 is complemented with an on-ground test rig. The demonstrator aims to reach TR6 in 2022. Laminarity flow control technologies, either natural or hybrid, can provide, when applied on wings, nacelle, and empennage, a reduction of up to 10% of fuel burn. We have three demonstrators in that field. The first one is on BizJet laminar nacelle, natural laminar flow applied to business jet horizontal tailplane, which is a demonstrator led by Dassault. The main objective of this project was to develop a laminar nacelle and a laminar empennage for business jet applications, with the aim to reduce the fuel consumption without increasing the cost of manufacture, despite higher surface quality requirements and without generating extra low workload for those maintenance technicians. All activities have been completed and the NLF synthesis has been carried out. The second one is the natural laminar flow smart integrated wing, which is a project led by Airbus. Clean Sky Breakthrough Laminar Aircraft Demonstrator in Europe, which is also called BLADE, led by Airbus, was flight tested in the context of the Clean Sky 1 program in 2016. The demonstrators aims at bringing about a 50% reduction of wing friction and up to 5% of lower CO2 emissions. Activities continued in the context of the Clean Sky 2 program with the aim to further characterize the technologies implemented in the context of the BLADE flight test campaign and to assess the results obtained for potential applications to the next generation of business jet or short-medium range aircraft. The activities will be completed in 2022 at TRL6 in the context of the Clean Sky 2 program. The third demonstrator is HLFC on tails and wing, which is a demonstrator led by Airbus. There are two technology demonstrators with potential application to long-range aircraft, which consist of the development of an HLFC demonstrators on the tail with the aim to meet TRL 5 and an HLFC demonstrator on the wing with the aim to meet TRL 4. The ambition is to develop the enabling technologies to mature the industrial process in order to fulfill the aerodynamic, industrial, and operability requirements and a simplified HLFC concept for high production rate aircraft at acceptable cost. Let's now depict the other flagship demonstrators which are in the novel aircraft configuration area. Here we have two novel rotorcraft concepts. The first one is a Racer, which is an Airbus helicopter-led demonstrator which combines an innovative wing box design with lighter structures and improved power management efficiency. Racer involves the use of forward propulsion through shaft-driven propellers on short wings, complementing the main rotor providing vertical lift and hover capability. It can cruise up to 400 km per hour. The aim is to meet TRL 6 in 2022. The second is the next-gen compound-tilt rotor, led by Leonardo Helicopter, which features a fixed engine, split gearbox drivetrain concept, with an advanced flight control system, efficient nacelle architecture, advanced wing architecture, and optimized tail configuration. It can cruise up to 500 km per hour. The aim is to meet TRL 6 in 2023. Another interesting demonstrator is the novel aircraft configuration and scale flight test demonstrator, which is led by research organizations such as ONERA, TU Delft, and DLR. This is a flight test model which could be used to investigate dynamic maneuvers and certain qualities that cannot be evaluated or validated properly in wind tunnel and iron bird test. This new innovative approach will pave the way for the design and development of new technologies such as distributed electric propulsion, which will be assessed on this novel platform, featuring 6 electrically driven propellers that will be installed on the wing. A scale flight test model, based on the optimized configuration, will be flight tested by 2023 to demonstrate the new configurations. In the innovative structure and production system area, we have a demonstrator which is called the multifunctional fuselage demonstrator, which is led by Airbus. This is an 8-meter-long fuselage barrel made from thermoplastic composites, a first of its kind worldwide. The multifunctional fuselage demonstrator deals mainly with reducing airframe weight and improving competitiveness of the domain, thanks to the design and development of new structures, mainly made of composite materials, and the associated manufacturing techniques, allowing the reduction of the lead time and supporting the increase of the number of aircraft to be produced every month, and the optimization of the maturing cost, including maintenance. This section is a section representative of an A321 with a section of 8 meters long, targeting the following ambitions: minus $1 million in terms of recurring cost, minus 1 ton in terms of weight, and a production rate higher than 70 aircraft per month. The final assembly will start in 2022 with the aim to achieve TRL 5 by the end of the program. In the area of intervention called Aircraft Non-Propulsive Energy and Control Systems, we have the demonstrator which is called Electrical Environmental Control System, which is led by LEAPR. This demonstrator aims at building architecture for environmental control systems based on electrical technologies to deliver the air cycle system, combined with an integrated vapor cycle system for increased cooling efficiency and an improved cabin environment. The ICAS demonstrator is developed around a specification based on a single-aisle short-medium more electrical aircraft type, and benefit of about 5 to 8% in terms of energy offtake is expected, which correspond to a 1 to 2% fuel reduction at aircraft level. This demonstrator is expected to reach TRL 6 in 2023. Another demonstrator is in the field of the non-propulsive energy, which is a demonstrator led by Safran. The Clean Sky Non-Propulsive Energy project focuses on new architectures that enable the aircraft auxiliary power unit, which is usually used solely to provide power when the aircraft is on the ground at the airport gate, to serve the demands of the next generation of more electrical aircraft by generating power during flight, not just on the ground. By having greater symbiosis between the main engines and the IPU throughout the entire flight envelope, energy savings are envisaged that will translate into environmental benefits for European mobility. This demonstrator is expected to reach TRL 5 in 2023. And the last but not the least, in the field of the next generation cockpit system. The DISCO demonstrator, which is an Airbus-led project, will demonstrate the capability of a large aircraft disruptive cockpit to run safely flight operations with a single pilot, with or without a flight assistant. It is the first step through the conception of a large passenger aircraft, cheaper, safer, and easier to operate with a better operational reliability. It will also allow to maintain Europe's aerospace industry leadership in a commercial aircraft and to develop the ecosystem of a European supply chain. Another demonstrator is also called Extended Cockpit Demonstrator, which is a demonstrator led by Thales, which features promising innovative cockpit solutions for greener and safer aviation. As an example, the seamless integration of a new generation of flight management systems will ensure not only improved efficiency, flight comfort, and lower direct operating costs, but also fuel savings, thus contributing to reducing the environmental impact of aeronautic by cutting CO2 emissions. These two demonstrators are expected to reach TRL 4 and TRL 5 by 2023. Let me provide you now some evaluation of results which are coming from the first assessment performed on the technology evaluator at mission level. In order to evaluate the environmental benefits of novel aeronautical technologies, several concept aircraft, 13 in total, have been defined as well as their reference counterpart for comparison. These concept models are addressing the four major market segments: long range with 2 aircraft concept, short range with 3 aircraft concept, regional with 5 aircraft concept, and commuter business jet with 3 aircraft concept. The methodology, as well as the detailed results at the 3 levels of assessments, are described in the reference document available on the Clean Sky 2 website. The results at mission level underline the fact that substantial progress has already been achieved and that the program is well on track. Most of the concepts achieve their target or even exceed them as given in the report. CO2, NOx, and noise emissions are reduced by 20 to 30% on most of the aircraft concept as compared to the 2014 reference aircraft considered for comparison. It is worth noting that additional improvements are expected in the second TE assessment that will be performed by the end of the program with inclusion of new technologies not yet considered in this first assessment due to the low maturity level achieved by the end of 2018. These are the areas which still deserve further efforts. On the SMR Plus, a CO2 reduction of minus 17% is achieved together with a NOx reduction of minus 34% versus the A321neo as reference aircraft. These aircraft first flew in February 2016 and entered into service in May 2017, and is 15 to 20% more fuel efficient than the A320neo family. Achieving an additional 17 CO2 reduction is therefore a substantial step forward. On long range, the LR Plus aircraft concept achieved a CO2 reduction of minus 13%, which is made versus the A350-900 as reference aircraft entered into service in 2015, a very highly optimized platform. This is a reduction which is therefore a substantial step forward. On the SMR++ aircraft concept, we achieve a minus 8% of NOx reduction, as the core engine model does not yet include low NOx combustor technology, unlike SMR+ model, which achieve minus 39%. Let's now discuss about the recent achievements which have been performed in 2020. Let's start with the Racer. After closing the critical design review in 2019, the Racer's detailed design review has been finalized in 2020, clearing the path for procurement and manufacturing of the key subsystems. In 2020, despite COVID-19 restrictions, Racer made good progress and major components were completed and delivered to Airbus Helicopter for the final assembly. Racer assembly is started at the beginning of 2021. Ground tests will start Q4 2021, Q1 2022, and flight tests are expected in the second half of 2022. On the next-gen compound tilt-rotor demonstrator, the development of the demonstrator started in late 2014. After the successful completion of the pre-design activities in 2016 and the preliminary design review completed in 2019, the demonstrator design was further matured in 2020. The critical design gate review at aircraft level started successfully in December 2020 and will continue along 2021. This has enabled the starting of the manufacturing of major components and subsystems such as wing, fuselage, fuel system, structural interfaces for the tail. The aircraft assembly and ground testing will be completed in 2022 in view of a full-scale flight testing in 2023. In the field of the regional aircraft, we have the Flight Test Bed 2 demonstrator. The status of this demonstrator is that design is closed and aircraft modifications are performed. The power-on has been performed. At the same time, ground demonstrators are fully operative, preparing in-flight demonstration. In addition, a pressurized wind tunnel test has taken place in 2020, providing valuable data for the platform. In the field of the PAX cabin demonstrators for regional aircraft application, the CDR was completed in December 2020. The PAX demo is a full-scale test bench representative of typical regional aircraft cabin, including major cabin system of the service area and most forwarded part of the passenger area. This environment will fully reproduce typical cruise flight conditions of the regional aircraft platform. In 2020, the critical design review for the integration of major cabins items in the full-scale demonstrator was successfully passed. In the field of the small transport domain, we have performed flight tests of elements manufactured with the new technologies. SAT, major activities are ongoing to develop innovative design process and manufacturing technologies in order to increase aircraft flight safety while reducing manufacturing cost. At the end of 2020, flight tests of the M28 aircraft with a composite engine nacelle were carried out, confirming the design assumptions and the suitability of the developed solution for future design applications in aviation, with a reduction of parts and joints used by about 35% and a reduction of components weight by more than 10%. In the field of hybrid electric architecture for more aircraft, we have the project called eMaestro, which is a continuation of the Maestro demonstrator. The goal was to mature the hybrid electric architecture's technologies for small air transport and to contribute to the achievements of the Clean Sky targets. After defining the engine requirements, the down selection of the most promising architecture was made, with the series Hybrid 1 being selected as the least polluting. In the field of the multifunctional fuselage demonstrator, we have installed the fourth generation of platform concept, the crown module. The crown module is the upper part of the fuselage that includes the ceiling area of the aircraft and hosts a wide variety of cabin components. In 2020, a model demonstrator of the crown module was tested in a representative environment. Semi-automated pre-assembly and integration of the module was successfully performed, bringing evidence for zero customization at airframe as an industrial approach and preparing the ground for further integration into the multifunctional fuselage demonstrator. In 2020, a maintenance review was performed on the TechTP demonstrator. Featuring a 7-blade propeller and a nacelle, it is representative of an aircraft installation. The review highlighted that all periodic maintenance tasks would be easily feasible, leading to variable recommendations for a better customer experience. We have completed the assembly of the scale flight test demonstrator. At the end of 2020, the activity mainly consisted in the integration of the many subsystems and overall testing, including flight test instrumentation, towards the completion of the scale flight test demonstration. On radical aircraft configuration demonstrators, a 6-blade propeller design has been selected mid-December 2020. The adaptation to the scale flight testing demonstrator to a distributed electric propulsion system version has been finalized with a feasibility report. We have recently passed the hybrid laminar flow control wing review, which achieved the TRL3. Focusing on HLFC on wing, further maturation of chosen technologies has been conducted, notably the selection of technologies and design solutions for what concerns the variable porosity, the removable outer skin of the leading edge, the complex CFRP substructure, and the inductive wing ice protection system. The TRL3 review was conducted successfully in October 2020. In the field of the extended cockpit, the demonstrator was completed. The overall extended cockpit was demonstrated in a ground lab environment and on a virtual system integration bench, thus achieving TRL5, including the evaluation of the following technologies: the next generation of eyes-out cockpit products, the intelligent natural crew assistant in several flight phases, the crew monitoring for drowsiness and incapacitation, and the use of an adapted pilot behavior monitoring system as an innovative test means for supporting avionics certification activities. The Smart Integrated Wing Phase 2 was completed. The activities started to produce more hardware for testing and integration into ground and flight demonstration. The Smart Integrated Wing demonstrator for large aircraft was equipped with additional electronic network and control components according to phase 2 requirements on top of the components provided through national projects. Innovative electrical flight control activities for regional aircraft completed the assembly of the first actuators, including the novel control units, and achieved component level testing before their delivery to the regional aircraft ground test rig for integration. On the environmental control system demonstrator, the CDR was passed. As a major milestone, the ECAS critical design review was held in 2020 with the airframer. The scope also included the combined vapor cycle system. Another main achievement is in the field of the outer wing box demonstrator. The advanced composite external wing box demonstrator will contribute to the flight test of the regional FTB2 in the regional IADP. With the aim to optimize the wing performance, wing box weight, and cost reduction in manufacturing, the demonstrator includes a goal to mature out of autoclave processing of automotive dry fiber place components using liquid resin infusion. An infusion system and tooling set for the lower skin, as well as the spare parts, have been installed at the Airbus facilities in Spain. The 4-meter skin is already produced, with the entire assembly ready to be produced within 2021 for the composite wing demonstrator. The final on-ground testing will be carried out in 2023 to achieve Tier 5 in this field. And the last but not the least, the 6 panels for fuselage structural demonstrators for regional application. The goal of this demonstrator is to develop an advanced composite technology base and integrated structural concept for fuselage applications in a cost-effective, competitive manner, especially taking into account the high expectation level of eco-compliance. The technological development contributes directly to the on-ground fuselage regional IADP demonstrator. The full-scale innovative composite stiffened panels is manufactured with the automated layup system developed. The manufacturing of the full-scale fuselage composite stiffened panels for both structural and PAX cabin rail demonstrator is ongoing. This completes my presentation, and I would like to thank you for your attention, and I will hand over the mic to my colleague, Ron van Manen. Ron, it's up to you.
So before we move forward on clean aviation, back perhaps to why such programs, Clean Aviation under preparation and the Clean Sky 2 program, as explained by Sebastien, my colleague, are so vital for the future of aviation. We know aviation has a track record in terms of safety, which is unsurpassed. We also know the phenomenal social value and the economic value that it has brought to society. We have a record in terms of economics and efficiency gains, which is hard to emulate from any other sector, with basically 90% plus improvement since the early jet age in the 1960s, as you can see in the graph next to me. But just look at what has happened since 1990. Available seat kilometers, a parameter for the volume of the sector, has tripled since then. Clearly, with the efficiency gains, we've made progress, but emissions in raw total terms have doubled in the same time. And this is a trend which needs to be broken as we look forward towards the middle of the century and a future of climate neutrality. Now, how we build our strategy for clean aviation will hinge on 3 aspects, and we need to look at the data in the air transport system to determine what the best way forward is. It's widely known that the majority of flights sit within the, what I would call, short range and regional aspects of aviation. It's also widely known that in passenger numbers, the wide majority is also in that segment of the market, but a little bit more balanced as larger aircraft carry people to further destinations. What is often assumed, however, is that fuel burn tends to lie within the longer range segments. Here, data from the International Council on Clean Transport, the ICCT, from just before the onset of the COVID-19 pandemic. And what we see is quite revealing. What we see is that 1/3 of aviation's emissions actually come from flights below 1,500 kilometers, 2/3 from flights below 4,000 kilometers. And this is quite telling in terms of where the opportunity is to make a start. The second aspect here is what I would call the window of opportunity. When we look at the current fleet and the newest clean sheet designs that have entered the market, across the spectrum of aviation, the bar has put at a very high level, looking at the A350 from Airbus, the Boeing 787, in terms of their efficiency. And taking a new big step forward is likely to take considerable time compared to other areas of opportunity, most notably single-aisle aircraft for short, medium range, and regional aircraft. So there's an industrial aspect that leads us to focus on the short haul, the medium segment, and on regional aircraft. And the third dimension here is what I would call technology push. A number of initiatives at what I would call the lower end of the spectrum of aviation is pushing technology in ways we've never seen before. This is, so to say, the new revolution in aviation. Over 150 initiatives, privately funded, are pushing at the lower end, if you like, of urban air mobility, small regional travel. And the technology being used may not become immediately effective for long-haul travel, but it for sure will be able to be scaled into regional and partially into short-haul aircraft. So that technology revolution is coming, and it's coming, I think, within the time frame that the Clean Aviation Program can help us make decisive steps towards the future of aviation and its sustainability. Now, that means we're going to see what is often mentioned in the press as battery-based electric flight moving into mainstream. Now, it is our view that the battery solution will remain limited to quite short segments and small aircraft. But that does not mean that electric flight will be limited to only those segments. Fuel cells powered by hydrogen can make the same entry into the market, but can be scaled much more aggressively towards regional aircraft. Beyond regional aircraft, we're likely to see the traditional gas turbine, although traditional is only a manner of speak, remaining the backbone of propulsion for aviation as we move forward. But clearly we've seen on the inside of gas turbine engines phenomenal advances, and we'll see more as well. These systems will coexist. We will see future gas turbines. We are convinced that another 20% of performance can be eked out of the systems based on aero engines, gas turbines. And when we combine that with sustainable aviation fuels, we can make a decisive step towards sustainability in the medium and long-range segments. But hydrogen has a role to play, which we believe needs to be progressed now aggressively on the research roadmap towards our future. So the Clean Aviation Program is building a roadmap based on three main thrusts. Based on the opportunity area of short, medium range, and regional transport, based on the technology push, and based on the opportunity that hydrogen as a zero carbon fuel can bring us. The program will work on the next generation of regional aircraft, the next generation of single aisle, short and short medium range aircraft, and will work aggressively on proving the viability of hydrogen as an energy source on board, whether through fuel cells, probably in the regional domain, through a hybrid architecture, or combined with fuel cells and gas turbines towards the larger area of this broad spectrum of regional up to medium range aircraft. It's worth noting, when we look at the targets that we are setting for the Clean Aviation Program, together with the industry stakeholders, together with the European Commission on behalf of the European Union, is that there is total alignment between these program goals and the focus, and a broader initiative announced this spring called Destination 2050. Destination 2050 involves the airlines in Europe, the air navigation service providers, the airports, and all major manufacturers. And the Clean Aviation Program will aim to double the pace, and I'll return to that in a moment, double the pace in terms of the technology gains that we can effectively put in the market. Over 30% improvement in single-aisle, short, medium-range aircraft. 50 or more % improvement in the regional area. And the prospect of zero carbon flight by using liquid hydrogen as onboard energy source. So how will we get there? Those of you who are entering a career in aviation need not worry in terms of what you've done in your university days. The same laws of physics will apply. We will need to push the envelope in every area where we've done this before, in terms of aerodynamic efficiency, in terms of the structural weight, the mass of the aircraft, new materials, new structural concepts, in terms of the propulsive efficiency. And perhaps more so than in the past, we'll look at the fuel itself, and that fuel parameter will have consequences that will flush throughout the entire aircraft design philosophy. So we need to keep pushing the envelope in all of the traditional aeronautical sciences, as I just explained. But on top of that, we'll see what I call non-traditional sciences making an increased contribution towards the future aircraft architectures. This will range from electrical power generation, where we'll see the transition from more electric aircraft, like the 787, to future designs where electrical power forms part of the propulsion, or at the smaller end, even becomes the full propulsion system. And in this area, we'll see multi-megawatt systems on very high voltages playing a critical part with new technological challenges. Other sectors will help bring in this competence and knowledge, and we'll need to translate that into aviation-grade technologies in terms of safety, reliability. Thermal management will play a role. Picture an aircraft with liquid hydrogen on board at 20 Kelvin, or electrical engines producing several dozens of kilowatts of heat, regardless of their very high efficiencies. Energy management, enabling hybridization, will be one such role. And we'll see more distributed systems and distributed intelligence and autonomy across systems within the aircraft. But to get these aircraft in the market at the speed in which we need this to be done, as Axel referred to in terms of urgency, basically replacing up to 75% of the fleet by 2050, we need to make sure that we have a manufacturing system that can produce aircraft at scale and with a speed and at a level of affordability that airlines can absorb and fly profitably, and manufacturers can produce with a profit. Getting there will require an increased use of digitization, simulation, new ways of certification in order to break the trend of ever-increased complexity and longer development cycles. And we'll need to look at the life cycle aspects, because by the time we're replacing such numbers of aircraft, we're talking about up to 50,000 aircraft being replaced within the 2 decades after 2030. The opportunity is huge. The scale of the challenge is tremendous. Axel already mentioned, we estimate roughly 12 billion in research required to get to this stage over the coming decade. Clean aviation can form a backbone for that research within Europe, but it will need all industry players, all funding authorities, national, regional, other parts of research at the EU level, to pool resources and to align roadmaps to make this happen. The development cycle after this research will be another challenge, with probably around 50 billion of investment needed for the segments that we're speaking about. But the business case is there. The opportunity to replace conservatively 25,000 aircraft over 2 decades is a 5 trillion euro opportunity for the aeronautic sector. And the business case is quite clear. This journey needs to start yesterday. As we move forward in preparing this program and preparing for a sustainable future of aviation, the who's who of European aeronautics is with us. Private industry, aircraft manufacturers, engine manufacturers, systems and equipment, the RTOs and universities have joined hands in preparing a roadmap together with the joint undertaking and the European Commission. When the program launches, there will be opportunity for many more to join, and we call on all those that wish to join to support this goal. Thank you.
Thank you, Ron and Sebastien, for providing this insight into the current state of play, as well as what we can expect in the coming years. Clearly, we are heading towards a very busy and exciting period for Clean Sky, for clean aviation, and the entire aviation stakeholdership as a whole. To build on Clean Sky 1's and Clean Sky 2's great technological progress through clean aviation, we need to continue to bring together the best of the aeronautics sector in the solid framework of a public-private partnership research program. We shouldn't underestimate the magnitude of the challenge ahead of us. We are speaking here about skipping a generation and leapfrogging into an N+2 commercial aircraft program environment. There's no time to spare. Bold, rapid investment in research and innovation is needed now to steer aviation firmly towards climate neutrality by 2050. We need to speak about impact also within the research community. Although the challenge ahead is tremendous, I firmly believe we have the competence and the capacity to succeed. The future of sustainable aviation looks bright. If you are curious to learn more about the innovative demonstrations we have achieved in Clean Sky 2, you can visit our interactive online stand, where you will find interviews with our experts, 3D models, and much more. And if you want to keep up to date with our latest news and follow the launch of Clean Aviation later this year, you can sign up to our newsletter and follow us on Twitter and LinkedIn. Thank you all for joining our presentation today, and I wish you all a continued exciting participation to the ICAS Congress over the coming days. Thank you.